Hey guys, welcome back to our YouTube channel. Today we are going to look at a very familiar topic. We're going to look at survivor analysis, and we are going to do it in Stata. Last time we looked at how to do Kaplan-Meier curves in R. Today we are going to look at how do we do survivor analysis in Stata. So first of all, what is survivor analysis? This is just a branch of statistics that deals with the analysis of time to event data. So the whole idea, it focuses on estimating the time until an event of interest occurs, such as death, disease recurrence, equipment failure, all anything that requires time. So we collect data in a way in a longitudinal way that from the beginning until to when our event occurs. For example, we might collect data from when patients are being admitted until they die or until they get an outcome of interest. This data kind of analysis can also be used in social sciences and other fields. For example, you can determine the time for maybe someone from leaving campus or university to getting a job. So when your outcome of interest is getting a job, or maybe time taken from students to get a bank account. So survival is just a statistical term. It doesn't mean that someone has to be dying. So it is not related to death. So what are the key concepts of survival analysis? We have time to event data. This data that we record time until an event occurs. We follow up participants until we see an event. So we have censoring. It can be left or right censoring. So this simply means that the event of interest has not yet occurred for some subjects during this study period. So what do I mean by this? For example, if we decide to follow up participants from maybe when they are admitted to a hospital until they die, and we say we are going to have a maximum follow-up time of maybe a month, and we see we are going to follow up these accident victims, for example, until from the admission until they die, but our maximum follow-up period is 1 month. So some people might die on day 1, others on day 2, day 15, day 30, but you might find that some are still alive until maybe day 35. So in our study, since we set the maximum follow-up time as 30, in our study they are still alive even though they died on day 35. So you see that we have to include a maximum follow-up time for such a study. So we also have what we call a survival function, or in bracket ST. It's just a probability that an individual survives from the time of origin or the time we start to follow up this participant to a specified future time t. Then we have others like a hazard function. This is the sustaining rate of at which an event occurs given no prior event. So we have Kaplan-Meier estimates. We saw them in our previous video. Then we have the Cox Proportional Hazard model. We are going to focus on this in this video, the Cox Proportional Hazards model. This is a semi-parametric model used to assess the effect of covariates, all independent factors, on the hazard rate. So we have graphical means that we can view our survival data. For example, we have the Kaplan-Meier survival curve, we have the life table and things like that. So today we are going to concentrate on the Cox Proportional Hazards model. So this Cox proportional hazard model, or normally called the Cox or Cox PH model, is widely used in survival analysis to examine the effect of covariates or independent variables on the time to an event. For example, you want to know what is like the risk of maybe age on death, on time to death, something like that. However, since it is a semi-parametric model, we have, that means, the parametric and the non-parametric model. So this is in between. So for any model of choice, you have to first test its assumptions if it fits the data. So in this whole video, we're going to test the assumptions of a Cox PH model. So some of the key assumptions, we have the proportional hazards. So the effect of covariates is constant over time. That's what it says, that the effect of covariate is constant over time. Then we have the linearity, which means the relationship between covariate and the log hazard is linear. So how are we going to test these assumptions? First of all, we are going to test the first assumption of proportional hazards assumption, which states that the hazard ratio between two individuals remain constant over time. So this is just a mathematical expression, and you can see it's a mathematical expression that the hazard of variable 1 over hazard of x2 is the exponential beta x1 minus x2. So we test this method used by plotting using the Schoenfeld residuals. So this graph includes a plot showing Schoenfeld's residuals against time for age. I chose age because we are going to use age as our example. So please note that in proportional hazards or the Cox PH model, the data we can have continuous variables and categorical variables as anywhere else. So we don't treat these two variables the same way, as we are going to see. So let's go to our data. So this is a data set of I think, it was MDR TB, all multi-drug resistant TB. So we were following up participants from admission until they die. So they were followed up for a maximum period of 2 years or 24 months. So we shall use it time as 24 months. That's the time, the maximum follow-up time. So as you can see, this is our outcome. If we can see, only 55, that's a lot, 11.70% of participants died during this whole time. So we can't take this proportion as a prevalence of death or a mortality rate, because it doesn't account for time, because not everyone died at the same time. So if you just report the mortality rate is 11.7%, this is wrong. You are not taking account of time. People are not dying at the same time. So this is one of the uses of such analysis. It is used in analyzing mortality data. So first of all, we need to first set our data to survival. So you go to statistics, survival analysis, decay data, survival. So our time variable is the time in months. So let's include the ID. This is an option, but we are going to include it because we want to calculate each follow-up time for each participant. For each participant, what we call so let's set our outcome, and the failure is 1. So I said I put 1 because as a failure, because it's what we want to look at. We want to look at death. So death is our main outcome. So that's why I put failure as 1. Okay, so we have already declared our data as survival data. So we can go ahead, though we looked at already the Kaplan-Meier survival curve, we can look at it again. In survival graphs, Kaplan-Meier survival function, we have the failure function and the survivor. So we are looking at the survivor function right now. just select this first option, and here we are. So it shows how patients, the probability of survival on this y-axis versus analysis time, the 24 months, the probability of survival over time. So we shall see this in detail. I think we saw it in detail, but I think you know also something called the life table. You can also see how it looks like. I think it is in graphs. You can also add in statistics tables. We can see life table, survival data. Okay, we can now set our time to time in months and our failure variable as outcome we want on the table. Yeah, so this is what we call the life table. It's the interval 0 to 1 is like a 0 to 1 month, because these are months. So we begin with 470 people, 5 people died, we lost 0. This is a survival rate, and this is 95% confidence interval. Month 2, 1 to 2. So if we want to find the median survival, so we can look at the median time, which is 12 months, this one, and we have the median survival as 93%. So at the median time, 93% of the participants will still be alive, which is good. So that's the life table in summary. So though that's not our main reason for this video, so let's look at let's first summarize the age, because we are going to look at the assumptions. And I told you that the continuous variables and categorical variables are treated differently. So by summarizing our age, we can see that the mean is 34 and standard deviation is 12, minimum is 1, and the maximum is 84. So let's draw a histogram and we see how it looks like. A histogram of age. We want the normal curve, the K density, and it's a frequency histogram. So this is the normal function, and this is the K density. It is it's a bit normally distributed, though the K density shows a bit of little skewness. So as you see from this histogram, if you wanted to categorize this age, what would you do? Personally, I would categorize as less than 20, from 20 to 39, from then 40 to less than 60, and above 60. I would do that because that's what I would. Many people would do. Let me categorize it for you now. I'll show you why I'm doing this later. So let's categorize it as from minimum to 19, less than 20, 20 to 39, 40 to 59, and 60 plus, and we call it age cut. So that's the age category. So if we tabulate age cut, we can see these are our categories we have created. We shall see later why it is necessary. So then we go to what we call the proportional hazards assumption. So let's test our first assumption of proportional hazards, and by doing that, we are going to first run a Cox regression analysis for the age. You see the hazard ratio is 1.04, and the p-value is significant. So we can say but for every increase in age, it is associated with a 4% increase in the risk of death. So if we plot we plot this, you see that normally if this it is supposed to, it doesn't have to show a pattern, so that's why this is supposed to be around this scattered plot, I mean dot should be around this line. So but as you can see now, it's like showing it has some pattern. So between 0 to 5, and as the next time increases, you see that it scatters away. Then we have this. So I will show you why we need to do that, because we have now, we see that we have violated one of our assumptions, and we shall see what we do when we violate the assumption. So we have the assumption of linearity. So the covariates have a linear relationship with the log hazards. So here we also plot the martingale residuals. So include a scatter plot of martingale residuals against of edge against a lowest curve. So let's do that. First of all, we are going to run our regression, our Cox PH model of, then we estimate, we get the estimate of a null model. Then we plot, we predict the martingale of a null model. After that, we get a graph, a two-way graph of a scatter graph of martingale against edge. Then we put a lowest of martingale against edge with the legend on. As you can see, like I told you last time, it shows a pattern that as edge increases, you see that there is a pattern of increased pattern. So this also tells you something. Either the edge is associated with time. As edge increases, there is the hazards might increase, or it can also show, it can also tell you where to categorize from if you want to categorize this data. So everywhere you see a point or an elbow is where you're going to categorize from. So as we can see, we have like a 20 or less than 20, then 22, 59 or 60, it's around there. So this is where we are going to categorize from. Remember, we categorize using histogram. Now we are going to categorize using what the data is telling us. So normally, people want to categorize data by just thinking, eyeballing. But the problem with that is that not all data is the same. So your data might be different from someone else's data when someone else categorizes the age differently. Unless if it is known in literature that age between this and that is associated with death, and it is consistent. So that's when you categorize using that age. But other than that, use what your data tells you. So let's categorize using what our data has told us, and we call it age cut 2. So by tabulating age cut 2, you see we get 30, 472, and 13. Let's see what we got here. Here we had 4 categories. Now we have 3 categories. So this is going to send us to another concept, what we call time varying covariates. So by this we mean that time varying covariates is the one whose effect on the hazard rate changes over time. It means like the effect of age, for example, on the hazard rate or on the risk rate, I may call it risk rate, changes over time. Maybe when people are young, the It's not the same risk as people when people are old or when people are mid-aged, something like that. So how do we do this? We can manually create an interaction term between the covariate and time, or we can use a Stata command which has a TVC, time varying covariate. We shall see why we need to do both. Now we have this is a Stata command for a time varying covariate. We include comma TVC. So we see that the time varying covariate using the Stata command, it is not significant. But if we create the time varying command by ourselves, by generating age time, and so if we generate age time and we multiply age by this time of analysis, you see it here, time was dashed, we have created it. So let's run a Cox model using that and we see what happens. You see that when we create our own time varying covariate, the hazard ratio for age changes and also the time varying covariate is significant. So one might ask why, because it should be the same ideally, but here it shows different. So when you use the inbuilt Stata command, so there is a way the software goes on determining the time varying for this age, for this continuous variable on its own. And when you use it manually, when you create the time varying covariate manually, you have more control of the variable because you have created it yourself. You have multiplied it manually. So this happens if you can do this if you don't have a complex variable, complex data. If your data is simple like this one, it's a simple data set, there is no reason why I'm going to use the TVC for Stata. But then let's see what happens. So if you run this, we're going to see which one is a better model. Either what Stata give us or our age time we have created. When you run this, it is okay. You can first store estimates. So let's store estimates as a TVC model. Then let's run our own. Then store estimates as the age time model. So if you want to know which one is a better model to use, whether the TVC for Stata or the one we have created ourselves, we can then do a likelihood ratio test and we determine which one has the lowest AIC and BIC. So if we see the age time, our model we have created has a lower AIC and a lower BIC than what Stata is giving us. That means our model we created is a better fitting model for this data than what Stata is giving us. So you see why now we need to test both. Although it's not a rule that you must, it depends on the data you have. So the second example we can have, we have another continuous variable which is called the duration of symptoms. So duration of symptoms is from 1 to 96. So we see that this was measured in weeks from 1 to 96. So if we create we run a Cox Proportional Hazards, a Cox regression model, we see that there is for every duration of someone who is on treatment, reduces the risk by maybe, is it 1%, and it's statistically significant. But this is in weeks. So let's plot a two-way plot for martingale residuals and this, and we see. So you see also there is a pattern. So as time goes on, there is a reduction on the hazards. So it tells us to categorize here and maybe here at less than 40 and between 60 and 70. So let's do that and we see. Let's categorize at less than 40, and I'm going to show you why I'm doing this. So we called it duration on treatment cut. So it has given us 3 categories. But then you might want to create this duration of treatment as months instead of weeks, because we have done this in months. So let's divide this by 4.34 and we round off by 2 decimal places. So we have created a new variable of duration in months. It is from 0 to 24, and the observations are those, and we see that the mean is 11, standard deviation, the mean duration of treatment is 11, standard deviation is 5. So now let's run this ST Cox for both, and we see where is the difference. So when you run the ST Cox for both months for duration of treatment in weeks, it gives us 0.93 as the hazard ratio, and duration in a month, it gives us 0.73. You'd think it would give us the same, right? But no. Now, to determine which one is a better one, let's plot a martingale residual, a two-way plot of martingale residual versus time, and we see what we get. So it also gives us the same pattern. It is telling us now to categorize between 5 and 10. This is like 8 or 7, below 7. Then, right, someone would say here or here at 18 months. So I categorize this. Okay, this is R. I categorize this as less than 6 months, 7 to 17, and from 18 and above. So we shall see, let's see what the duration in weeks was giving us. There's a big difference. Okay, so then let's get a better model for this, and we see which one is better, categorizing as months or as weeks. So we run the same thing. We store estimates for both. So let's store estimates first for the duration in months as this, and we store the estimates for duration in weeks as this. So then we'll run the likelihood ratio test. Remember, we have done it here. We don't need to. By the way, if you want to know how to get that likelihood ratio test, you can just use the Stata menu. You go into post estimation, you go in tests and contrasts, then you go to likelihood ratio test for comparing models, and you launch. We have a duration and duration in months. So you can include the statistical information, display information, and force sometimes when it refuses. So yeah, so we see that the model for months is better, has a lower AIC and BIC. So we drop the model for weeks and we take one with months. But before we do that, let's first see another assumption. That is testing for categorical variables. So categorizing age into age groups and checking proportional hazard model, that's what we're going to do. So we include a sample plot showing the log, negative log of survival curves by the category of any of the covariate. So let's do that and we see. Before we select, we see that here now the model is telling us to take this one out. We shall see. Let's see what our by doing that. Let's first do one for age categories. There are two things I'm going to do here. This is for age category 2 that the model told us to categorize from. So let's plot STH plot by age and we see. So this plot is supposed not to join, or it's supposed to show a parallel relationship, that these don't join each other. So if they don't join each other, that means the assumption is fulfilled. This is the first age category 2 that the model told us to categorize from. Let's see for the age category that we categorized using the histogram. First, we shall first run the model for each category. Then we run the assumption. You see, now this one, they cross. So meaning, this is not a better, by graphical means, this category we created by just viewing the histogram violates this assumption. Let's see if this goes with the statistical assumption, and we see. So for the first one, we are going to run this and store estimates. So let's store the estimates as age category. I hope we haven't done that before. Yeah, okay. Then we run this as age cat 2 and we store estimates as age cat 2. So then let's run a likelihood ratio test of age cat. Let's see if these two things say the same thing. We can see that age cat 2 has a lower AIC and a lower BIC than age cat. Remember, age cat 2 is the one we categorized using what the model told us to do, to categorize from. And age cat is the one we categorized using the histogram, the eyeballing thing. So you see that they both coincide by saying that the one that the model told us is better. This is a very big reason that I tell students and everyone that does analysis that normally follow what your data tells you, not what you think. Some people might think, maybe those people who are younger, maybe they will die of fast. You don't know that. People are different. Maybe in your setting, it is the other way around. It's the young ones that are living, and not the old ones. So it is better to follow what your data tells you. So that means we are going to drop the age category, the cat that we created using histogram, and we follow this. But remember, we had a time varying covariate. So let's see if by doing either by categorizing we eliminate the time varying. So if you want to create a time varying, you can do the Cox edge cut, comma TVC, remember we have dummies. So we see that by using TVC there is no statistically significant edge category by using time varying, and we can see that our hazard ratios up here are very wild. This is because, let me show you why they are wild. Because we have only 13 participants, 2.77. We shall see how to fix this. But now, if we are to create it manually, okay, we can first also run a likelihood ratio test to see if edge category 2 versus edge, how did we name it? Edge time model. Which one is better? Edge time model. So by running, we can see that edge time model is better fitting for this data than the edge cut tool. But then we haven't done the time varying for these categories. Let's do it. Let's first do it, and we see we have 1 is representing less than 20, 2 is representing this, and so let's create edge time 1. Oh, my man was going to R, so let's generate edge time 1 as equal to time. Okay. So this so is edge cut. Where is it? Edge cut 2 is equal to 1 times, we create time varying for each edge group, and we see. Okay. So for time 2 is equal to 2. What? There's 1, 2, 4. How did that happen? Okay. 3. Okay, let's run the Cox Proportional Hazard again by including this time varying covariates for each edge group. You see it's a mess. That means, yeah, it can't work. The first model is the better one. So this can't work, and the reason is this is the reason, like I told you. 13 people here. So we can always fix this. You can add them to this group, or use a continuous variable. Like we saw, the continuous variable with the time varying covariate is better. Yeah, we shall use that for our main analysis. So yeah. So for the duration, let me do also for duration. So we say the duration with the monthly category is the one that is better. So let's run it and we see. Then let's generate the plot. Oh yeah. So this is also a mess. Oh no. Sorry. Supposed to do for category, not the continuous variable. Yeah. Oh yeah. This is great. They don't cross. So which means this is a very good this was a very good nice categorization for us. So we have seen all these assumptions, how to do them. We have seen how to get along with the proportional hazards assumption, the linearity assumption, time varying covariate, testing for categorical variables versus the proportional hazards. Then let's determine the detailed pH, or what we call the global test. So the global test is for, you can include every variable in the model that you want to test. Then you test for the p-values, if they are significant or not. If they are significant, for every, it means the assumption is violated. So we're only going to include only two variables, just as an example. So you see that for sex, age, it is not violated, the assumption. Test for proportional